Welcome class to our guided notes section on the Skill 8 part of our Unit 4 Skill 7 through 9 guided note outline, where we begin first with some simple multiplication or division. So I threw some division in a little early before we get to Skill 9, just for these simple ones because they act the same way as multiplication does. And then in our next video, we'll look at the more difficult Skill 9 type of problems. So this video is really focused more on multiplication, or Skill 8 from our Unit 4 skill set. So let's get to it. So basically, when we are multiplying or dividing radical expressions, we normally need to have the same index, at least for this outline, because we haven't learned yet about rational exponents. So there will be more on that coming soon in our next module, which will be the week after spring break. We will learn about rational exponents and how we could work with indexes that aren't the same. But for simple radical expressions, multiplying and dividing, they have to have the same index in order to follow the rules we're about to show you. Okay, so same index for now. Then you basically multiply outside numbers with outside numbers, okay? So it's all about location. You multiply or divide the numbers outside with each other, okay? And then also you multiply or divide the numbers inside with each other. So outside with outside, inside with inside, and then at the very end you simplify. So it's very straightforward. But again, make sure that before you do this, that they have the same index. When the index is different, there will be different set of rules to follow, and it will come in the rational exponents outline, which is actually skill 10. Okay. So let's take a look at example 5. So we're multiplying fourth roots, so the indexes match, which means we can follow the rules outlined here. And there aren't any numbers outside, there's only numbers inside, so we can just basically multiply them together. So to sum up, you can multiply things inside a radical to each other. You can multiply across a fourth root as long as the index matches and as long as it's multiplication or division. You just go ahead and combine it all under one fourth root sign. So maybe I'll write it that way for this very first one, just so you can kind of see. We're going to do 3 times 5 all under the same fourth root. And then n times n to the 7th, all under the same fourth root. So it's kind of like you're just combining them under one radical sign. And so that works with multiplication or division. And then we're going to go ahead and simplify, okay, or multiply and simplify. 3 times 5 is 15. N to the 1st times n to the 7th would be n to the 8th because we add the powers. We're multiplying the n's, and the exponents are telling us how many factors of n we have. So when we're multiplying, we're just adding up all the factors basically. So there's 8 total factors of n. Now we're going to go ahead and simplify because that means there's enough to take a perfect fourth root. So maybe I'll just write this the long way again, just because it's the first one, and then I'll kind of use shortcuts from here on out. Well, 15 I know came from 3 and 5, and 3 and 5 are both prime numbers, so there's definitely not going to be 4 identical factors that I can find a fourth root of, so I'll leave 15 alone. But the n, there's 8 factors, right? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 factors, which means you can break that up into 2 groups of 4. And every time you have an indexed size group, that's a perfect fourth root, or a perfect root of whatever the index size is. In this case, it's a 4. So I have 2 perfect fourth roots of n, right? So I can, for every time you have a perfect root, you can take it out of the radical. So I can take one n out and then another n out, and then I'm left with a fourth root of 15. Or this is n squared times the fourth root of 15 when you simplify. So that would be my final answer right there. Now what's the shortcut? So this is a reminder back to skill 6. You can take 8, which is the power in the radical, and divide it by 4, which is the index. So you can take powers and divide them by indexes to get the remaining exponent once you fourth root. So fourth rooting is basically saying divide this into 2 groups of 4, basically. So 8 divided by 4 is 2. That's the shortcut. Okay, let's move over to number 6. So in number 6, we have the same index again, right? These are both square roots. So that means we can go ahead and follow these steps of multiplying outside with outside and inside with inside. So the outside numbers are 3 and 4. Again, let me write this the long way, just since it's our first time doing this. So the outside numbers get multiplied together and they stay outside the radical. And then the inside numbers get multiplied together and they stay under the radical as well. So then I end up with 12 times the square root of 20, because 2 times 10 is 20. But that can be simplified. So I need to simplify it further. In fact, maybe I'll go back to here when it was 2 times 10 and then break the 10 into 2 and 5. So really, the square root of 20 is 2 times 2 times 5, right? 2 times 2 times 5. And then the fact that I have 2 identical factors under a square root indicates a perfect square root. A perfect second root, right? It's an indexed size group. So I can pull that out of the radical sign and then multiply it to the 12 that's already there, because now this becomes an outside number. So then 12 times 2 multiplied to the square root of 5, and so I end up with 24 times the square root of 5 in simplest form. But I do want to point something out, because one thing we'll be looking for, like on our tests and quizzes, will be equivalency. And so I want you to recognize that these expressions are equivalent. If you plugged them into a calculator, they would give you the same decimal value. Okay, so these are the same numbers. Numerically, they are the same. But just this one is in simplest form in terms of the expression, the way it's written. These number quantities are identical, they're equivalent, but this version with the 24 times square root of 5 is the simplest form in terms of the algebraic expression. Okay, then let's take a look at number 7. So everything right now is under the radical sign. So that means that all this stuff is going to get multiplied together. But we are going to have to simplify at the end, so it might be in our best interest to not actually multiply everything, but more keep track of what's there. And then after we simplify, we can begin to multiply remaining things. But first notice that they're both square roots, which is why I can combine them all under one large square root. So I'm going to start with the numbers. I've got 72 and 10. I'm not going to multiply those together yet because I can tell that there's definitely perfect squares in there that I can take out. So I'm actually going to leave it in factored form, if you will. And then with the x's, I think I will go ahead and combine them initially. Maybe I'll write it all out first. So x to the 11 times x, y to the 6th times y to the 3rd, and then z to the 5th times z squared. And then we'll keep track of all these factors. Okay, now let's maybe begin with the numbers. So 72 can break into 8 and 9. 8 can break into 2 and 4. 9 can break into 3 and 3. And then 4 can break into 2 and 2. So I can see actually 2 perfect square roots of 2 and 3. And then a single factor of 2 will have to stay. Or will it? Or will it? Because if you look at the 10, look at this. The 10 has another factor of 2. So actually, this single factor of 2 will be able to pair with this factor of 2 over here, and really only a 5 will remain under the radical. Let me write that out the long way so you can see kind of what's going on there. If you notice, there are, between the two numbers, there's actually 4 factors of 2 between the two, right? So I've got 2 times 2 times 2 times 2 if I combine these 3 2's from the 8 and then that 2 from the 10. Meanwhile, I have 2 factors of 3 that came from the 9 and then a single factor of 5 that came from the 10. So when I put all of those factors together, that gives me the number of 72 times 10. Let's just do a quick check just to make sure that that's true. So I just went over here to calculator.com and I did 2 times 2 times 2 times 2 times 3 times 3 times 5. and that equals 720, which would be the same thing I would get if I multiplied 72 times 10. So 72 times 10 basically consists of 4 2s, 2 3s, and 1 5. So we got that covered. But now I can see with those 4 2s, the 2 3s, and the 5 that I have 1, 2, 3 index size groups, right? I've got 3 perfect square roots. One of 2, another one of 2, and then one of 3. So let's look at our x's and our y's and our z's. So I wrote little plus signs in here because basically when you're multiplying same bases, you're adding the powers. So that means I have 12 factors of x, 9 factors of y, and then 7 factors of z, 5 plus 2. So let's see how many perfect squares I have in there, right? Because every time you have an index size group, that's a perfect square root. So for x to the 12th, let's just take a look at that one over here. So I could think of x to the 12th as x squared times x squared times x squared times x squared 2, 4, 6, 8 times x squared times x squared 1, 2, 3, 4, 5, 6. I could think of this as 6 groups of 2 or 2 groups of 6. That's another way you could think about it. You can think of it as x to the 6th times x to the 6th. See, 12 divides evenly by 2, so that worked out really nice. The reason I split it up into 2s is because every time you have an index size group, that's how many perfect square roots there are. So basically I had 6, right? 6 perfect square roots of x. That's one way to think about it. That's kind of how we thought about it in our Skill 6 video. But because 12 does divide evenly by 2, you could also just put it into one pair, right? So that's a perfect square root right there. So this is a perfect square root of x to the 6th. Right? Because it's 2 identical groupings of x to the 6th, or 2 groups of x to the 6th. Either way, what happens is you end up pulling out x to the 6th. Either you pull out 6 single x's out in front of the radical, or you pull out 1 x to the 6th. Either way. Then for y to the 9th, maybe we'll look at this one right here. I'll break it into perfect index size groups. So 2, 4, 6, 8, and then I'd have a single factor of y left over, right? Because 9 doesn't divide evenly by 2. But I do notice that it has 4 perfect index size groups. I have 4 perfect square roots of y. 1, 2, 3, 4. Because every time you have an index size group, that's a perfect root of that index. So this is perfect square roots, 4 of them for the y's. And then for the z's, I'll pull those down here just to make sure we have enough room. So z to the 7th would be z squared times z squared times z squared 2, 4, 6 times z to the 1st, right? 2 plus 2 plus 2 plus 1 is 7. So that means I had 3 perfect square roots of z. 1, 2, 3. For each index size group, that's 1 perfect square root. Okay, so then what does this all simplify down to? Well, I can pull out, so what does this all simplify down to? Well, I can pull out a 2, a 2, a 3. I can pull out an x to the 6th, or 6 single x's, right? 6 perfect square roots of x. I can pull out 4 y's, and I can pull out 3 z's. Because anything that has 2 of the same factor counts as 1 square root and can all come out of the radical. And then what stays in the radical was a 5, a single factor of y, and a single factor of z. No x's because 12 divided evenly by 2, right, and got 6. 12 divided evenly by 2 and got 6. The y and the z had powers of 9 and 7, so they did not divide evenly, but there were still perfect squares within them. So I took out 4 factors of y, 3 factors of z, but there was 1 factor of each remaining under the square root. So 5yz. Okay, so then all of this gets multiplied together on the outside. So I've got 2 times 2 times 3, which is 12, x to the 6th, y to the 4th, z cubed, times the square root of 5yz. That's our final answer for number 7. Now, some of you might be wondering, maybe, do I need absolute value here? And the answer is no, because the only variable that would have potentially needed absolute value would be the x right here, because it had an even power under the even root, the even index, right? But when it's simplified, it was still even. The only time you need absolute value is if you start with an even index, continue with an even power, and end with an odd power. Since that didn't happen here, we don't need absolute value for the x. Meanwhile, since the powers of y and z were odd, they automatically become exempt from needing an absolute value. So let's take a look at some division. Basically, it works the same way as multiplication. If the indexes match, then you can go ahead and divide numbers that are under the same index with each other. You can combine them over one radical, or under one radical sign, as long as the index matches, which it does here. So 40 divided by 5, we can go ahead and do that division, and that's 8. And then we simplify at the end, just like we did with the other ones. So 8, as we know, is basically 3 factors of 2, right? 2 times 2 times 2. So the cube root of 8 is 2. So the cube root of 40 divided by the cube root of 5 ended up being the simple number of 2. All right, let's take a look at number 9. So with number 9, it doesn't look like anything divides necessarily, right? 3 doesn't divide into 25 and x can't divide into y. So what I wanted you to know is, like, you can also do the same thing we just did in 8, but backwards. So when everything is combined under the same radical sign, but it's a division or multiplication, you could actually split it up and think of it as 2 separate radicals. So you can combine them together under one radical sign if the index matches, or split them up under 2 separate radical signs with the same index. And the square root of 3x squared can be simplified a little bit, and the square root of 25 y to the 16 can be completely simplified. I'm going to use the division method here because both of these divide evenly. So I'm going to do 2 divided by 2 to get 1. And 16 divided by 2 to get 8. So this is 3x to the first, right? That was 2 divided by 2 over, that's a square root of 3. The x can come out of the square root, but the 3 cannot. And then the square root of 25 is 5, and then 16 divided by 2 is 8. That's 16 divided by 2. Let me rewrite this a little bit. So I've got x to the first times the square root of 3, all over 5 times y to the 8th. And then in this particular case, I am going to need to put the x under absolute value because the index was even and the power of x under the radical sign was even, but when it divided, it became odd, which means it could potentially be negative, which means I need to put absolute value around it to keep it positive. And so that's my final answer for number 9. Now looking at number 10, I've got, again, division. I've got numbers outside the radical and then numbers inside the radical, and the indexes match. So that means I can go ahead and simplify according to our rules, which is outside with outside and inside with inside. So 12 divided by 4 can be 3. And then I can combine the 18 and the 6 all under the same 4th root sign. So that means I get 3 times the 4th root of 3 because 18 divided by 6 is 3. Now the 4th root of 3 cannot be further simplified, so this one is done. But basically, the point of this example was just to show outside numbers get divided with each other. 12 and 4 divide to 3. Inside numbers get divided with each other. 18 and 6 also divide to 3. Lastly, in this video, I wanted to talk about when you have to multiply radical expressions with 2 terms, right? Not just single terms, like in examples 11, 12, and 13. So basically you FOIL. Okay, that's basically what we do. We add any, or we simplify any radicals if possible, and then we combine like terms. This is through addition or subtraction if we end up with any like terms. That means same index, same radicand. Okay, but we always begin with FOILing. So we'll do that with example 11. I'm going to distribute the 3 to the square root of 10 and the square root of 5. And then after that, I'll distribute the square root of 2 to the square root of 10 and the square root of 2 again to the square root of 5. So it would look something like this. 3 times the square root of 10 plus 3 times the square root of 5. I couldn't actually multiply 3 with 10 or 5 because 3 is considered an outside number and 5 is an inside number. So they cannot be multiplied together. They're just sort of written next to each other like this. Okay. But when I do the square root of 2 times the square root of 10, that I can combine all under the same radical. Same thing when I do the square root of 2 times the square root of 5. So I've got 3 rad 10 plus 3 rad 5 plus the square root of 20 plus the square root of 10. So I can see already some like terms emerging, right? The 3 square root 10 plus 1 square root 10. I can combine those together to get 4 square root 10 because this is technically a 1 in front and I add 3 with 1. Now here, the 3 rad 5 and the rad 20, I need to see if maybe I can simplify the square root of 20. And it looks like I can because 20 can break into 4 and 5. 4 can break into 2 and 2. Which can be pulled out of the radical. So let's see what we've got here. Let me just erase this for 1 sec and write this out again. So I've got 3 rad 10 plus 3 rad 5 plus 2 rad 5, right? Because the 2 from the square root 20 can come out. The single factor of 5 stays in, and then I have my 1 square root of 10. And then I recognize, like I pointed out earlier, that I have like terms right here with the 3 rad 10 and the 1 rad 10, but then I also have like terms with 3 rad 5 and 2 rad 5. So that ends up equaling 4 rad 10 plus 5 rad 5. And that is my final answer for number 11. So we FOIL, we simplify, and we combine. Let's try it again with number 12. So I'm going to distribute 2 rad 3 to rad 3. And then 2 rad 3 to 6 rad 5, and then 4 rad 5 to rad 3, and then 4 rad 5 to 6 rad 5. So for the 2 rad 3 to rad 3, I can multiply the 3's together since they were both inside numbers. And then with the 2 rad 3 and the 6 rad 5, which is actually negative because this is a minus sign right there. So that should be minus. So 2 times 6 can go together to make 12, and then 3 times 5 can go together to make 15, plus 4 times the square root of 5 times 3. 5 and 3 can multiply together, and then minus 24 times the square root of 5 times 5. So this is 2 times the square root of 9 minus 12 times the square root of 15 plus 4 times the square root of 15 minus 24 times the square root of 25. Well, right away, I hope you're noticing it, but I've got some perfect squares, right? 3 and 3, that's the square root of 9. 5 and 5 is the square root of 25. So this is really 2 times 3 minus 12 rad 15 plus 4 rad 15 minus 24 times 5. Because once you square root the number, you multiply the square root to whatever's in front. So 3 gets multiplied to 2 and 5 gets multiplied to 24. Meanwhile, these guys both have a square root of 15, so I can combine those together. Those are like terms. So I have 6 minus 8 times the square root of 15 because I added negative 12 with 4, so they actually subtracted to get 8, and it's negative 8 since the 12 is bigger, and that's the one that's negative. And then minus 120, 24 times 5. So that leaves me with some more like terms, right? 6 is an integer, negative 120 is an integer. I can combine them together and get negative 114 minus 8 times the square root of 15. And that's my final answer for number 12. Lastly, with number 13, we have, again, we're going to start by foiling. Okay, so we're going to do, let me rewrite it so we can actually see what we're doing. So I have 8 minus the square root of 80 times 5 minus the square root of 5. So I'll do 8 times 5, and then 8 times the negative square root of 5, negative square root of 80 times 5, and negative square root of 80 times negative square root of 5. So that gives me 8 times 5 is 40, minus 8 times the square root of 5. So those 8 and 5 cannot actually multiply because 8's outside and 5's inside. So we just write them next to each other. Minus 5 times the square root of 80, and then minus the square root of 80 times 5. That, in that scenario, this one here, actually that should be a plus. Sorry, that should be a plus because negative times a negative makes a positive. But in this scenario, the 80 and the 5 can be multiplied together since they're both inside. Okay, so now let's do some simplifying because 80 I know can be simplified, right? Because it just has a lot of 2's in it, I'm sure. Let's start with the first one. So 2 and 40, and then 2 and 20, and then 2 and 10, and then 2 and 5. So I have 2 perfect square roots of 2 that I can pull out. And then on this one here, I can do the same factors, right? 2 and 40, 2 and 20, 2 and 10, 2 and 5, and then there's another 5. So not only do I have 2 perfect square roots of 2, but then I also have a perfect square root of 5, because when you combine the factors of 80 together with 5, you end up with 2 5s. So let's see what we got here all together. So now we've got 40 minus 8 times the square root of 5 minus 5 times 2 times 2 times the square root of 5 plus 2 times 2 times 5, because there's nothing left in the square root for this last expression. Let me keep going there. So now I have 40 minus 8 rad 5 minus 10 times 2, so that's 20 rad 5 plus 20 again, right? 2 times 2 is 4 times 5 is 20. So then I notice 2 sets of like terms. I've got 40 as an integer and then 20 as an integer. But then I've also got negative 8 times the square root of 5 and then minus 20 times the square root of 5. Those both have matching index and radicands, so I can combine those as well. So the 40 plus the 20 would give me 60, and the negative 8 plus negative 20 would be negative 28 rad 5. And that would be my final answer for number 12. So, or number 13, sorry. So as to recap these ones with the binomials, it's you foil first, then simplify the radicals. So we simplified, then combine like terms. Foil, simplify the radicals, combine like terms. And that's how it's done when you've got binomials. So this concludes our Skill 8 video. Let me know if you have any questions on the practice. Thanks.